somehow got delayed. So do you mind waiting for 5 minutes? Thanks. Yeah, sorry. Yeah, no problem. Okay, let's start. So today I want to continue doing stuff that we started last time. So basically we saw what, roughly speaking, the classes P and NP were. We tried to, we posed this question P versus NP. So today we're going to study this notion of NP completeness. So let's do a quick recap. Okay, so the last time we started off with this question that how do we go about proving low bounds on algorithms? Okay. And the reason we said it was non-trivial is because you want to show low bounds that hold for any possible algorithm. Okay. And that's why it's usually tricky. And we saw that for one example, which is sorting when you're only allowed certain kinds of operations. We saw that n log n was the best possible. Okay. And this was via this clean argument, but it turns out it's one of a kind. So there are not that many good low bound proofs. So very often what we resort to doing is by saying, okay, this problem is as hard as this other problem which many people have tried to solve but could not solve. Okay, so that's what we do. And so in that context we defined the notions of P and NP. So we defined them in an informal way last time. We also defined this problem of Boolean satisfiability. Okay. So this was where you have a formula and it has n, and it's made up of n Boolean variables. Okay, so we call them x1 through xn. Boolean just means true false variables, and you have a logical formula. Okay, so and you want to figure out if there exists an assignment. So if there exists a setting of these x1 through xn to true or false, such that the overall formula evaluates to true. Okay, so that's what's called the Boolean satisfiability problem. And if you remember, we said that the trivial algorithm takes 2 to the n time. And we said that one of the big open questions, which is a way of phrasing P versus NP, is if there is a polynomial time algorithm for this satisfiability problem. So this is what we saw last time. Then we started out defining the notion of reductions between problems. We said, we defined informally what this notion is. So today we'll go more formally into these definitions, and we'll try to do a better job of what we did last time. So this pen has this issue that if it's not connected, it thinks my hand is the pen. That's why. Alright, so let's recap quickly what P and NP were. Okay, so we said that P is the set of all problems that can be solved efficiently in polynomial time. Okay? So here we are talking about actually solving the problem. And NP is the set of all problems for which, given a solution, you can verify it in polynomial time. Okay, so that is what is NP. And this is an informal definition. Okay, and we said that this is more powerful. I mean, a lot of things that you would imagine can be in NP, right? So any puzzle, for example, is in NP because given a solution, you can usually verify whether whether it's the right solution or not. Okay, so this and mathematical proofs, I should say proofs, are also like this, in the sense that given the proof you can verify if it's correct or not, but how you come up with the proof is the tricky thing. Okay, so these were P and NP, so we'll probably define them a little bit more formally this time. Okay. And what you should know is that these are examples of what are called complexity classes. Okay, so note that P and NP are both a class of problems, right? So it says a set of all problems. Okay, and so all the problems in the world you can try to categorize them. Okay, and this is what this figure tries to show. Okay, so P is somewhere here. I don't know if you can see this, but yeah, so P is somewhere there, and P is this bigger thing, the yellow circle, right, and so on. Okay, so and there are lots of other complexity classes. Okay, and one of the favorite jobs of complexity theorists is, given a problem, try to figure out where it lies. Okay, so these are just some examples of classes. Okay, so there are a lot more of these. So this is just to give you an example of what kind of things people do. Okay, so before we go on, I want to say that, from the purposes of complexity, we usually think of problems as what are called decision problems. Okay, so far what we've seen are mostly optimization, right? So we said that what is the maximum value of some function, or what's the best way of doing something, and so on, right? So for the purposes of complexity, we usually think of just decision problems. Okay, and most problems you can actually phrase them as decision problems. Okay, so one question that's naturally a decision problem is the satisfiability problem. Okay, so satisfiability, we have a formula phi. This is what I'll call the SAT problem. So you have a formula phi, and you ask, is phi satisfiable? So, and by this we just mean, do there exist values of variables such that phi evaluates to true. So this is naturally a yes/no question, right? So sometimes you could have problems that look like optimization questions, like this maximum independent set problem. Okay, so where you have a graph, you want to find the maximum number of nodes such that no two have an edge between them. Okay, so this is a maximization problem, but you can phrase it as a decision problem by saying that, oh, does this graph have an independent set of size k? And if you can answer such queries, you can also solve the maximization problem, because you can say, you can try all possible k, or you can do a binary search, something like this. Okay, so usually in complexity theory we are interested in decision problems. The reason is that it makes life a little bit simpler. Okay, so basically, if all the problems are just decision problems, right? So then you can think of a problem as just being the set of all instances for which the answer is yes. Okay, so I don't know if you can see this, but so this way of doing it allows you to think of any problem as simply the set of yes instances. Okay, so you can just think of a problem as a set of instances, which is nice mathematically, right? Because instances are just strings of a certain length. And you can say a problem is basically the set of all yes instances. Okay, so it's just a subset of strings. This is mathematically very clean to think about. Okay, so this is why people usually consider decision problems. Alright, and last time we said we are going to study this notion of reductions. Okay, so we said that for many problems we won't be able to show lower bounds, and we are going to basically show that one problem is as hard as the other. Okay? And one application we said why we want to do this is maybe you want to satisfy your boss, right? So maybe you want to convince your boss that it's not just you who can't solve this problem. Okay, so this is what we saw last time. But should remember the goal of reductions is usually to say that one problem is as hard as the other. Okay. But clearly this is not our only motivation. Mathematicians don't care about their bosses. So what we really want to do is you want to figure out how hard problems are relative to each other. Okay, so this is the main goal in complexity theory. So this is why you saw all these circles which some of them overlapped and so on. Okay, so basically you want to figure out, you want to define equivalence classes of problems. You want to say that these problems are exactly as hard as each other. And you want to say that, oh, okay, this problem is strictly harder than these guys and so on. Okay? So building this kind of hierarchies of problems is what theoretical computer science is all about. Okay? And actually, if you think about it, it's somewhat surprising that these kind of equivalence classes come about, right? Because for all you know, every problem could have its own complexity. Okay, so a priori there is no reason that problems should be equivalent to each other. Okay? But that's the beautiful thing. So it turns out that a lot of problems are equivalent to each other, and there are only a few kind of classes of problems. Okay? So few at least interesting ones. Okay? So this is one of the reasons also why we study reductions. Okay, so how do we formalize a reduction? Right? So remember that our goal is to say that you have two problems, call them problem A and problem B. Both are decision problems, and which means the answer is just yes, no. Okay? And you want to say that that problem B is as difficult as problem A. Okay? So what does this mean? So how would you formally say this? So I want to convince you that problem B is at least as difficult. Okay, so let me write that in case it's not clear. I want to say that it's at least as difficult as problem A. So what does this mean?
If you can solve it, show us a problem B which is equivalent to A.
So this is one try, right? So you can say that if you can solve A, you can solve B. But this is showing that A is easier than B is easier than A.
Yeah, but at least
right?
it's the other.
Yeah, so this is actually the other way around. So this is one thing you should be wary about when doing reductions. This is the first mistake everybody who does complexity for the first time does. Is you reduce in the other direction. Okay, so this is what you should not do. So if you want to show that problem B is at least as difficult as problem A. Okay. So we are saying that B is harder than A, okay. Which means that if you can solve B, you should be able to solve A. Okay. So this is so we should show solving A. Okay. And what does this mean formally? So how would one prove such a statement? That if you can solve B, you can solve A.
So that you can reduce B in set A to B.
That's true, but like intuitively, let's say you, what does it mean to say solve A, right? So you want to build an algorithm that solves a
set, and then we can generalize it to numbers.
If you have a subroutine that solves B, you can use it in an algorithm to solve it.
reduce evenly. Yeah, so what he said is if you have some form of a subroutine, okay, so let's say I give you a black box that can solve the problem B. Okay. Now the question is, can you make some queries to that black box and come up with an efficient algorithm to solve A? Okay. So this is one way of formalizing this, right? So suppose there is a black box. This is also called an oracle. So suppose we have a black box. To solve B. Okay. Can we design an efficient, that is polytime, algorithm for A? Okay. So this is the question we want to ask. Okay. So if you have a oracle for solving B, okay, so can you then use this oracle? You can query it on any input you want, and you are allowed to play with the outputs of this oracle. And can you use it to solve B? Okay, so that's what's called. So this is one way of formalizing. And this turns out. So is this notion of reduction clear? That you just have an oracle, a black box for solving B, and you want to build an algorithm. So the algorithm could say, oh, okay, so you get an input, and it could say modify the input in some certain way, and then you call B, the oracle for B on that input, and do something with this answer. You could call this oracle multiple times, and so on. Okay. So these are what are called Turing reductions. So these are. So this is one way of formalizing the notion of reduction, and these are called Turing reductions or Cook reductions. Okay. So Steve Cook is a mathematician. Okay, so that's why, and Turing, of course, is Turing. So yeah, so both of them kind of studied these kind of reductions, and so these are called Turing or Cook reduction. Yeah.
If there is an efficient algorithm for A, working a black box for B, means that A is harder than B.
Doesn't it mean that what?
Yeah, A is a harder problem than B.
No, it's so what does it mean intuitively to say A is harder, right? So it means that if I can solve A, I can solve B.
Like, say for example, the black box is some algorithm in some time that solves B.
Yeah.
And this.
You're saying this takes more time.
Yeah.
Because this could call it multiple times and so on. But we are saying harder in a polynomial sense. Okay, so this algorithm is supposed to be efficient, right? So what this shows is that time of B, time of A is less than or equal to poly of time of B. Or poly in the input times the size than the time. Okay, so this is all this says. Okay, this is what I mean by easier. Okay, so this is in terms of I'm allowed to lose some polynomial factors. Okay, so this is how you should think about it. So yeah, that's a good question. So the running time could be a little bit higher, but it's not much higher. So this means that A is easier than B. Okay. So any other questions?
Could I ask one just to clarify his sort of, so
Yeah.
is he saying that using the black box to solve A would take longer than just running the black box to solve B? Was that what he was asking?
No. So what he's saying is maybe this algorithm for A that we came up with here, it uses the black box for B 100 times. Okay. So you are saying that the algorithm for A is 100 times slower than the algorithm for B, right? So in some sense, it's slower. I mean, it's slower. I guess that's what he was getting at.
Yeah, so
Yeah.
since it's slower, doesn't it mean that A is a hard problem?
Not necessarily. So we measure hardness in terms of polynomial losses. Okay, so we don't care if. So we are okay giving up a polynomial factor. Okay, so all we want to say is if B can be solved in polynomial time, then A can also be solved in polynomial time. Okay, so if there is polynomial, just means some n squared, something like this. And so what this says is, suppose you had an oracle for B that could solve it in, let's say, n squared time. Okay, now A can be solved maybe in n to the 100th time, but it's still polynomial. Okay, so that is all we care about most of the time in complexity. Okay, so we don't care about the exact thing or, oh, this is 100 times slower or something like this. Okay.
So what you're saying is, suppose like B is solvable in n cube time,
Yes.
A is solvable in n power 4 time, it doesn't mean that A is harder than
No. Yeah, for these purposes it doesn't mean. So what we are saying is, so they are just polynomially equivalent to each other. So they are all in the same complexity class. So yeah, so this is an important point.
Do we decide the hardness based on complexity? Running time?
So the hardness of a problem doesn't depend on the algorithm, on any specific algorithm. So so it's a property of the problem itself. Okay, and so maybe you can come up with an algorithm that runs in quadratic time. Maybe somebody can come up with an algorithm that runs in linear time, something like this. But that's not what we care about. Okay, so we only care about whether it can be solved. There exists some polynomial time to solve it, something like that. Okay, so this there exists is important, and this is why it's very difficult to rule out whether a problem is in P or not. Okay, because you want to say that there exists some algorithm, or you want to show that there exists no algorithm that can solve this in polynomial. Okay, so that's why it's difficult. Okay. Yeah, so that's a good point. So any other questions? Yeah.
So does that, can you reverse the problem by saying that if you solve B, then there you can solve A? So what if you're given a set of problems, A, B, and C, and you're saying that they both have the same level of difficultness? Does it matter which one you pick, or because then your condition might change, right? If you say that you have to solve A in order to solve B with a polynomial time.
So, but how is C plain? I don't understand.
So that's the saying that I have 3 problems that have the same level of difficulty. Does it
Right.
matter which one you solve?
Right. So in this sense, saying that a bunch of problems have the same complexity is like saying, given an oracle for one of them, I can solve any of the other problems using that. Okay. So and formally, all that will show is that time for any problem is some polynomial of the time for any other problem. Okay. And that I'm happy with. Okay. So I'm happy paying a polynomial loss. Okay. So yeah.
So problem solving is to prove that problem B is as difficult as problem A, right?
Yes.
So isn't it enough if we show that both problem A and problem B belong to the same complexity class?
Well, sometimes, but that could be harder to show. So that way you are saying basically that there is some other problem C such that both of them kind of reduce in both directions to C. Okay. So you can think of this notion of reduction as you have. Actually, I might need a. So you can think of this as you have problem A, you have B and C. Now, A reduces to B is like saying this. Okay, so in the sense that if you have an oracle for B, you can solve A. And so what you are saying is both of them are in the same class, which means that there is some C such that A reduces to C and C reduces to A. Okay, so this is when you say that A and C are in the same class. So you didn't explicitly say what being in the same class means, but what it actually means is there is a reduction in both directions. Okay, So there is some, the class C is defined by some problem, and there is a reduction in both directions from A to C and C to A. And the same is true for B. This is what you would need to show to say that these two problems are in the same class. And then it is true that one can be reduced to the other can be reduced to this. Okay? But what I am saying is just one direction. Okay, so I am saying something much more basic. I am just saying, how do you show that one problem can be reduced to the other? Okay, and I am saying if there is an oracle for one problem, then you can solve A using calls to that oracle. Okay, so that's when we say that A is easier than B. No, I said you can phrase it any way, right? So you can say the problem statement is showing that A is easier than B, or saying that B is harder than A. Okay, so they are both the same. Okay, so it's like saying if you have two numbers, A is smaller than B, is like saying B is bigger than A, right? So the way I wrote it is, yeah.
A is as hard as B.
No, I said B is at least as hard as A. Okay. So it's one of these logical things that you have to think about for a little bit. So basically, if I want to say B is at least as hard as A, okay, mentally you can say B is bigger than or equal to A is what you're trying to say if there were numbers, right? It's like saying A is smaller than or equal to B, which means it's like saying A is easier than B. Yeah.
So then if you show B is at least as hard as A, have you reduced B to A or have you reduced A to B?
No, so this is what I did, right? So this is what you need to do. Basically, if you have a way of solving B, suppose you can solve A. Then intuitively you are saying that A is an easier problem to solve than B.
No, I understand that.
Yeah.
The terminology, which one are you reducing to the other one?
You're saying the terminology of what do I mean by reduce to?
Yeah.
Okay. So here I am reducing B to A. Okay. No, sorry. In this case, A to B, yeah. The thing about this is you say this enough times, you jumble. So, yeah. So I'm reducing solving A to solving B. Okay, so that's how you should think. Okay. So, okay, but what I want to emphasize here is that here I'm allowing you to have an oracle for B, and you are allowed to call it a polynomial number of times. Okay? So this is the notion of a Turing reduction or a Cook reduction. Okay? So now I'm going to tell you something which conceptually is probably a bit easier. So, but it's very similar, and these are what are called instance transformations. Okay? So I'm going to tell you about a different notion of reduction. Okay? It is stronger than the previous one. Okay? So earlier I said that we're going to see how these two are different in a bit, but let me define this stronger reduction first. Okay? So what I want to say is, I want to say that A is, so remember my goal is the same. I want to say that A is easier than B. Okay, so I want to say 1, A is easier than B. And I want to say that one way of showing this is to say I take some instance of A. Okay, so let's call this IA. And I want to say that it can be transformed into an instance of B. Okay, so remember both A and B are decision problems. Okay, so they both IA is either a yes or a no instance of A. Okay, so and I want to have this guarantee that IA is a yes instance for A, if and only if IB is a yes instance for B. Okay. So everyone familiar with this if and only if notation? It just means implication in both directions. Okay, so if the first statement implies the second statement implies the first. Okay, so that's what if and only if is. And you need the property that IB is polynomial in IA. Okay, so I want to say that this is a stronger notion of reduction in the sense that I guess intuitively this makes more sense. I mean, this is easier to grasp than the previous one, right? Because what you're saying here is, so I want to solve A, right? What does that mean? I get an instance I sub A, and I want to tell if it's a yes or a no instance. Okay? So let's say you want to build a machine that want to solve A. Okay, so I get IP, and goal is decide yes or no. Okay, sorry, IP. Right? So I want to solve problem A, so I get some instance for A. So now what will I do? Okay, so suppose I had a transformation algorithm like this. Okay, so suppose I know a way of transforming. Okay, so then I'm going to use this transformation to construct IB. Okay. And now if I assume that B can be solved, okay, so then there is an oracle for B. So I feed this oracle for B. So I feed this IB to this oracle, and I get the answer. Okay, so maybe it is yes. In which case I can just answer yes to this problem. Because the guarantee I have is that IB is a yes instance if and only if IA is a yes instance. Okay. So this is one way to, so this is an easy way, I mean, way of reducing A to B. Right? Because, so what you're saying is, if you can map every instance of A to some instance of B such that this condition holds, then you've reduced solving problem A to solving problem. Yeah.
If IP is value of IP, then does it mean IP is value of IP?
Yeah, that is true. But but what you want is for every IA, there is an instance IP, right? So there might not be any mapping in the other direction. Okay. So let's see a very kind of a simple example maybe that illustrates why you could have only one-sided reductions. Okay, so I hadn't planned on this, but sorry?
Any substring problem can be.
No. So you shouldn't think of it as just strings for now. But here you just think of them as instances, right? So I want to give an example where I reduce some easy problem to SAT. Okay, so let's do that. Okay, so what's your favorite easy problem?
Sorting.
Yes, so sorting is an easy problem, but sorting is not quite a decision problem, right? So you could have a decision version of sorting where you have an array and you want to answer if it's sorted or not. Okay, so that's a very easy problem, right? So I want to reduce this to SAT, okay, and say that for every instance of sorting, there is an instance of SAT such that that instance is yes if and only if the answer to the sorted question is yes. Okay, and how would you do that? Actually, you can easily come up with this. So
Linearly scan it at any place the successive two numbers are not in.
exactly. So you could have this SAT formula that basically says AI is bigger than A1 is less than A2 and A2 is less than A3 and A3 is less than A4 and so on, right? So this in some sense is a SAT formula. Okay? And what you're saying is that, and you have this if and only if condition. If the array is sorted, then this is true, this evaluates to true, and otherwise this evaluates to false. Okay, so this is, it's not, have to be more formal in this, but you can imagine how you can reduce easy problems to very difficult problems. Okay, so yeah, I guess you should think about this. What I said is not quite a reduction, because SAT usually, it's a question of satisfiability, right? So it's not as easy as this, but you can easily come up with things like this. So, all right. So But yes, so what I want to point out here is that this notion of reduction is different from the previous one in the sense that here you're taking some instance of the first problem, okay, and you're mapping it to a different instance, to an instance of the new problem, okay, so or of the different of problem B. Okay, and you're saying that this is yes if and only if this is yes. Okay, but okay, so one thing to keep in mind is that you might not be able to figure out if the answer to either of these two is yes or not efficiently. But all you can guarantee is that the answer to this is yes if and only if the answer to this one is yes. Okay, so this is the cool thing about reductions that you should keep in mind. Okay. But yes, going back to how this compares, here it's in some sense precisely one oracle call, right? And you are basically giving the same answer as what that oracle gave. Okay. So in this earlier, in Turing reductions, you are allowed to basically query this oracle multiple times, or you are allowed to change the answer of that problem and so on. Okay, so in that sense, these two notions of reduction are somewhat different. We'll just illustrate this with an example. Okay, so let's do that. Okay, so these are what are called carp reductions. And they are called so because they were made famous in this seminal paper of Dick Carp. So we'll get to that in a bit. Okay. So I want to just to highlight the difference between these two reductions. So what I want you to do is consider two problems. Okay. So one is what I call SAT, the other is unsat. Okay. So SAT is, we've all seen this, given a Boolean formula phi. Does there exist an assignment such that phi in variables x, does that phi of x assignments to x's such that phi of x is true? So this is a yes-no question. Now unsat is just a complementary problem. Okay, so here also you are given a phi. Does there not exist any assignment? Okay, so does there a sat assignment, satisfying assignment? So note that these two problems are exactly complementary. Okay, so if the answer to SAT is yes, then the answer to unsat is no, and if the answer to and the other way around. Okay. So intuitively, you would say that these two problems are as hard as each other, right? Because if I have an oracle for SAT, and I get a new formula, and I want to show that unsat is easier than SAT, then I could say that, okay, let's say I have an oracle for SAT, I get some formula phi, I just call that oracle, and if the answer is yes, I return no, if the answer is no, I return yes. Okay, so this is, and you can do the same for, to show that unsat is, or that SAT reduces to unsat. Okay, so you can do both-sided reductions if you are allowed this oracles. Okay, so in a Turing reduction sense, so these two problems are equivalent. Okay. Reductions go. SAT is as hard. Okay, so it's less than and bigger than, so it's as hard as and the other way around. Okay, so these two are equivalent in terms of complexity. But what about carp reductions? Right? So remember that in a carp reduction, what you want is, suppose I want you to show that I can reduce unsat to sat. So what are we saying? Okay, so what is, so this is the question you want to answer. Okay, so is there a car production that goes from unsat to sat? So what does that mean? Right, so let's say I am given this formula phi. Okay, so this is called phi 2. Okay, so there are some variables x1 through x4 or whatever. And what I want you to do is, given, so we are given an instance of this, and we want to come up with an instance phi prime of sat, okay, such that the answer to phi prime for sat is exactly the same as the answer to phi for unsat. Okay, so is the question clear? Yeah, maybe you should think about this for a minute before before you ask questions. So what we are saying is, given input phi for unsat, transform it to phi prime for sat, such that phi is yes for unsat if and only if phi prime is yes for sat. So try doing this, okay? So, and when you try doing this, the one thing I want you to think about, one way to think about this is by saying, I give you a formula, and can you certify to me that it's not satisfied? Okay. So can you give me, can you convince me that it's not satisfied? Okay. So note that this problem for SAT is easy, right? So suppose all I can do is polynomial time computation. Okay. And suppose you have a lot of time, you can do exponential time computation. Okay. But you can only give me a polynomial amount of information. Okay. Suppose two players play this game, and now I have a SAT formula. I want you to convince me that, let's say, firstly I want you to convince me that it's satisfiable. What would you do?
Try to find one.
So let me explain the game setup better. Okay, so you have, so there is a person A and a person B. So this kind of thing is always nice to think about in complexity. Okay, so there are two people. This guy can only do poly time computations. Person B can do exponential time. Okay, person B can do whatever he wants. Okay, but this guy has a formula phi. Okay. Person B wants to convince him that phi is satisfiable. So what should B do? So B can do whatever computation he wants. Is there an easy way he can satisfy A that this formula is actually satisfied? Yeah, so he can use brute force, B can use brute force to find the solution, and he can just give the solution to A. Okay. And A can verify this in polynomial time. Right? So note that this was essentially what NB was, right? So you have some solution and you just should be able to verify it. Right? So for SAT, you can do this. But what about unsat? Okay. So suppose I have a formula. So again, you have two people, A and B, and A has this formula phi. Now B can do any computation, but he needs to convince A that the formula is not satisfied. Okay, so how can B possibly do this? Yeah, so you've got to say that this formula is not satisfied, right?
Prove that complementary of that function is satisfiable.
that doesn't mean that the A is not satisfiable, right? So it could be that the complement has some solution, and this formula might have some other solution. Okay? So I mean, it's like a formula and its complement could both be satisfied, right? So that's the problem. Yeah.
Isn't it contradicting, because if there exists an input which can actually transform an unsat to a sat, then it was not an unsat problem in the first place?
No, so the transformation could produce a very different formula. Okay, so it need not be the same formula, right? So we are saying that phi, you transform it to some other very different looking phi prime. Maybe it has like a lot more variables, has something else, right? And all you want is this equivalence that that this is satisfiable. I mean that this is yes if and only if this is yes. Okay, so that's like saying this is not satisfiable if and only if that guy were satisfiable. Okay, and then you can see the equivalence between these two, like this game notion and this. Okay, yeah.
So he can't do it, right? Because person B can use exponential time to test every possible solution to discover that none of them satisfy it, but then he can't give a concrete solution that can be verified to person A.
Right, so he doesn't have to give a solution, right? So maybe he can do something else. Okay. So it turns out this is one of the big open problems in computer science. Okay, so this is what's called the NP versus co-NP question. Okay, so yeah. Oh right. Okay. So I have this title slide. Okay. So this is what is called the NP versus co-NP question. So basically, so is there a way of convincing someone that a formula is not satisfiable? Can you do it in polynomial time? Okay. So this we don't know. Okay. So we believe that this cannot be done, but there's no proof that this cannot be done. Okay. So it's very much like the P versus NP question.
But you can use anything to convince A. That means B is not restrained in what it can send A.
Yes, all it can send is some polynomial sized thing. Okay. So is there a poly-sized proof that phi is not satisfied? And this we don't know. So there are some ways of doing this. Okay, so there are these whole things called resolution-based proof systems, where you try to look at this formula and you try to like merge these variables and try to show that you get some contradiction out of it. Okay, so let's say the formula, a contradiction basically means you simplify this formula in certain ways, and then you end up with x and not x. Okay, and that clearly cannot be satisfiable. So these are what are called proof systems. So resolution is one of them, but not all formulas have short proofs using resolution. Okay, so there are formulas for which you might need to use exponentially long resolution-based proofs. Okay, so there's no short proofs of it. So this is one of the major open questions in complexity. Okay. And this kind of illustrates the difference between these Cook and Karp reductions, because if you look at Turing/Cook reductions, then SAT and unsat are trivially equivalent to each other. But if you just restrict to these Karp reductions, we don't know if these two are equivalent. And we actually believe they are not equal. Okay, so good. So now let's. So what I've said so far are they border on slightly philosophical. So you might want to go back, think about them. Okay, so actually the previous question we saw, it's this thing that comes up often in mathematics, where proving that some object exists is actually easy, but proving that it doesn't is quite difficult. Okay, and this is a common thing in mathematics. Like suppose I give you an equation and ask you to find a solution to it. Okay, so you could just exhibit a solution, but suppose I ask you to prove that there is no solution. It's often much harder. Okay. So yeah, so this is a common problem in math. Okay, so this is captured by this NP and co-NP. Okay, so let's now. Okay. So in the remainder of, so most of the time in computer science, in the remainder of the course and whatever in life and so on, when we think of polytime reductions, you usually just think of Karp reductions. Okay, so this is something that you should always keep in mind. If you say reductions without any quantification, people usually mean Karp reductions. And this is instance-wise. But it's good to know that there are these two kinds and there's a subtle difference between them. Okay. And let me also introduce some basic notation. So we say that problem A reduces to problem B. I write less than or equal to with a small p. Okay, so p is for polytime. Okay, so reduces to problem B if there is an instance transformation, like I said. Right? Okay, so if for all instances IA, there exists an IB of B such that you have these two conditions. Okay, so one, IA is yes if and only if IB is yes for B, and size of IB So these are two very important, these are the two important properties that you've got to check. Okay? And this is when we say that problem A reduces in polytime to problem B. Okay, and right, so now I want to define notions of NP-hard and NP-complete. So most of you would have seen this, but everybody should, you should not mess up, so let me formally define this. Okay, so this is what a reduction is, this is what a polytime reduction is, and this is what we called Karp reduction before. And yeah, so what is NP-hard? So problem P is said to be or problem Q, let's say. M1 P and P2. So it's said to be NP-hard. If what? So I guess you guys must all know. So let's. So when is what's the formal definition of NP-hard? So turns out, okay, so let me write the answer. So if satisfiability reduces to this problem, okay, so if satisfiability reduces in polytime to this Q, okay, so this problem is harder than SAT. So that's when we say the problem is NP-hard. So and what is NP-complete? Yeah.
I don't remember, but is it if the equivalence is both ways?
Yes, yeah. It's just that. Okay, so NP-complete basically means Q less than or equal to P SAT and SAT. Okay. So very often when you come up with a problem, you'll realize that showing this part is easy when you have a new problem. because most problems you want to solve are ones in which you can verify the solution easily. So you just have to figure out what the right variables are and so on, and then you can easily convert this to SAT. But reducing SAT to this problem is often the tricky thing. Okay, so we'll see a bunch of examples of that. But this is what NP complete is, and this is what NP is. So we'll probably see some examples in the homework of problems that are NP hard but not NP complete. Okay, so anyone know something off the top of your head? Yeah, that's fine. We'll see in the homeworks. Okay, so this is. Okay, so now let's move on to how you essentially show that problems are NP complete. Okay, so I want to give a few examples, and the reason everybody does this is because of this nice equivalence that I. Okay, so what this means is NP complete is a class of problems such that anyone can be reduced to the other. Okay, so using just these car products. Okay, and it says if one of them can be solved in polynomial time, then all of them can be solved in polynomial time. Okay, and one of these big conjectures in complexity theory, which actually people believe is false, is this notion of a dichotomy. Okay, so people think that all problems are all problems that are in NP are either NP complete or they are in P. Okay, so this is what is called the dichotomy conjecture, and people believe it's false, but we don't know of problems that you can prove are strictly between P and NP. Okay. So there are problems which we believe are like this, like factoring numbers is something that we strongly believe is like this, but we don't have a proof. So that's one of these interesting things. I mean, for such problems, the people who believe in this conjecture say that they are actually in P. Okay, so you can't find that algorithm, but there is a polytime algorithm. Okay, so there's a lot of this notion of equivalence is very nice. Okay, so this is the reason people study this. Okay, so let's go do this. So this is something I mentioned last time. Okay, so I said that so we won't prove this theorem, but I'll just say more precisely what CNF is. Okay, so the Cook-Levin theorem. This is something we mentioned last time. So basically, what it says is this Boolean satisfiability is NP complete. Okay, and the way I defined NP, this is a tautology. Okay, so the way I defined NP is by saying SAT reduced to this. So the way I define this is by definition. Okay, so they're the same problem, right? But yeah, so people sometimes define NP differently. So this actually requires proof. Okay, so if you define NP using Turing machines, then this requires proof. Okay, so that's why it's called the Cook-Levin theorem. So okay. So one thing I want to say is what this CNF means. Okay, so does everyone seen at least this notion of a CNF? Maybe you heard about it. So let me recap. Okay, so it's what's called a conjunctive normal form. Okay, so what is a conjunctive normal form? So how do you write a satisfiability formula? Right? So suppose I have some formula phi. I said it's a formula in n variables, so it will have so it has some n variables x1 or x2 bar. x2 bar is just not x1. Okay, so it's the logical not of applied to x1 or x3 and so on, right? Maybe there's an OR of something else, OR of x1 and x4 and so on. So conjunctive normal form is a special way of writing a SAT formula. Okay, so of writing a Boolean formula. Okay, so any Boolean formula. Yeah. I don't know if you always capitalize the B in Boolean or not, but people don't. Any Boolean formula can be written as an AND of ORs. So what does this mean? So I basically mean, so you have a formula, you have a bunch of ORs. So you have x1 or x2 bar or x3, and you have x4 or x1 or x2. You have a bunch of ORs like this. So OR of a bunch of variables. And you might have like x2 or x4. And these different ORs are connected by AND. Okay. So this is what is called the conjunctive normal form of a Boolean formula. Okay. So it's very simple. It's you have a bunch of ORs and you have ANDs connecting them. And it turns out any Boolean circuit you can write as in this form using without too much overhead. Okay. But it turns out there are simple Boolean expressions which might not have a short representation like this. Okay, but let's not get into that. Okay, so let's assume that you have a formula and it's always given in this form. Okay, so you have a bunch of ORs. Right now I'm not requiring each of them to be anything of any specific size. Okay, so some could have 3, some could have 4, and so on, and you have AND of them. Okay, so from now on, whenever I think of a formula phi, I will always assume that it's in this form. So, any question about this notation? It's just a notational convenience. Okay. Alright. And so essentially, Cook-Levin theorem says that this is if you have a problem of size, if you have a formula of size m in n variables, then finding a solution in poly mn is hard. Is exactly complete. Okay, so that's. And now we want to see a bunch of reductions. Okay. So as I said, this is the reason why they are called Karp reductions, because of this very famous paper by Dick Karp. This is, if I am not mistaken, this is the most cited paper in computer science. Okay, so it has some several thousand citations. Okay, so definitely one of the top 5. I don't know if it's still the top 1. It used to be the top for a while. But anyway, so what this problem came up with is, so it was one of these first papers that realized this notion of equivalence between problems. Okay, so what he said was, you have this popular problem, popular even by that time, problem of satisfiability, but he could show that there are all these whole bunch of combinatorial problems which on the face of it have nothing to do with satisfiability. But it turns out that they are all equivalent in terms of complexity, in the sense that there are reductions in both directions. Okay. So this is the cool thing that he showed, and in this paper, I guess these were one of the first few reductions that people came up with. Okay. So this was the non-trivial example. Okay. So I want to see a few reductions. Okay, so I want to start easy. Okay, so let's start with some very simple reductions. Okay, so let's start with. So I told you that satisfiability, I think of any formula as a bunch of clauses, right? So I said that it is a bunch of ORs connected by ANDs. each one is it's like x1 or x2 or something. Okay, so a bunch of all, and which are connected by atoms. Okay, so this is what is called a CNF formula. And so 3SAT, a 3CNF is a formula phi prime in which all these clauses, okay, so these are what are called clauses. So all clauses have size exactly 3. Okay, so that's what is called a 3CNF. Okay, so it's a formula where all clauses have 2 ORs, so it's like x1 or x2 or x1 and something else of size 3 and something else of size 3 and so on. Now, so what I first want to show is figuring out if, basically satisfiability for arbitrary CNFs is equivalent to satisfying the satisfiability for just these 3 CNFs. So the satisfiability problem just says you have a formula and you want to figure out if it's satisfiable. 3SAT is satisfiability formula, satisfiability problem, but restricted to inputs that are 3 CNFs. Okay, so those are the problems. Now I want to say that there are reductions in both directions. So which direction is easy? That's always the wrong thing, right? Because you so when you're thinking of reductions, by the way, this is the thing that I always do. So this is why I introduced this less than or equal to notation, because that makes this intuitive thing clear, right? So it's easy to say that 3SAT is less than P of SAT, right? Because this is a special case of SAT. Okay? So it's a special case of SAT. So this is easier. Okay? So the non-trivial part is what I wrote here. Okay? So you want to show that SAT reduces in polytime to 3SAT. Okay? So for that, so what do we have to do to show that SAT reduces to 3SAT?
Find a way to transform SAT to 3SAT.
Yeah, so you start with any SAT formula and you want to construct, so you start with some, so this is easy. Okay, so let's prove that SAT reduces to 3SAT. So which means you start with phi and you want to come up with a phi prime such that, so remember you have 2 conditions, right? So first is phi prime should be satisfiable if and only if phi is satisfiable, okay? And phi prime should be polynomial in phi. Okay. So how would you do this? Actually, let's make it easier. Okay, so note that this is often true in reductions. Okay, so suppose we could take one thing out here and create a 3SAT formula, okay, such that this guy is satisfiable if and only if the other guy is satisfiable. So can we do some clause by clause transformation? Okay, so that's one simple question you could ask. So this is one thing you often try to do when you are doing a reduction. You try to introduce things, do things locally. Okay, so do things one by one and so on. Okay, so in this case, it's particularly easy. If you have one clause, how do you try to modify it so that you come up with a 3SAT answer? So let's start with the simplest example. Okay, so x1 or x2 or x3 bar or x4. Okay, so suppose you had something like this. Okay, so this is one of the clauses. And can you come up with a new thing which actually which has the same satisfaction? You can combine variables. So you want to split this, right? So you want to come up with 3SAT formula. Okay. So ideally you might say, oh, maybe I'll try to split this, but then the satisfiability changes. I mean, in some sense, if you just break things apart, then the new thing might not be satisfiable, right? So this could be satisfiable, the new thing might not. So turns out there's a trick to it. So let me write down a formula, and you can verify why this is satisfied. Okay, so why these two are equal. Okay, so let me introduce a new variable z. Okay, and I'm going to look at these two things. So I'm going to say x1 or x2 or z, and z bar or x3 bar or x4. Okay. So I've just done what I wanted to do, which is split these two. Okay. And I introduced z here and z bar here. So I claim that any x1, x2, x3, x4 that satisfies this should also satisfy that, and the other way around. Okay. So in some sense, the z doesn't help you also. Okay. So why doesn't the z help you? Yeah. So suppose you set z to be true. Okay. Then what happens to the, so when is this thing true? When is the lower formula true? So I'm setting z to be true, right?
And both are true.
Yeah, so this is true, which means this is false, right? So if that guy has to now be satisfiable, either x3 bar or x4 has to be true, in which case even the top one will be satisfiable. Okay? And similarly, you can convince yourself that z was set to false, then this thing is true only if x1 or x2 is true. Okay, in which case that is also true. And the same in the other direction. If one of those things is, if the original one is true, then to set z appropriately, and then you can make this satisfied. So if you don't see this, just think about this for a bit after going back, and you'll see that this is true. So this lets you go from a clause that has 4 variables to 2 clauses that have 3 variables, right? So this is in the 3CNF form. So what if you had a clause with 10 variables? How would you do this?
Just introduce multiple new variables?
Yes, so you keep recursively doing this, right? So it's a simple exercise. What you have to be careful is not to introduce too many. Okay, so you just, the formula size should not blow up exponentially. Okay, so that is the important, remember when you are doing a reduction, you want to come up with a phi prime that has the same satisfiability, and also phi prime should have size that is at most polynomial in phi. Okay, so that is one thing you should be careful about. Yeah.
Is that complete?
Sorry?
Is that 3CNF problem complete?
Complete.
Like, I think it's incomplete. Like, I don't think that is.
No, if you had one clause, it's this. Okay. So what I'm saying is,
I don't think that class is equal.
what do you mean?
I think they should be two different.
No, so if I had just that one clause, then they are actually the same. Okay. So if you take any assignment to this, you can find an assignment to that. And if you take any assignment to that, you can find a valid assignment to this. Okay. So yeah, think about it. So if I start with any feasible assignment to the bottom one, can you find an assignment to the top?
It's double.
So what is z there?
So the 1 on 1, the x1 is 1, x2 is 1.
Yeah.
X3
So then both are satisfiable. So what you want to say is, if there is a satisfying assignment to the top one, there is also a satisfying assignment to the bottom, and the other way. That's what you mean by equivalence.
But it is not like if the value is yes for that, the value is no.
No. So what does it mean to say that that this formula is satisfiable, right? So it means that there is some assignment which makes this true. Okay. And in this case, the same assignment happens to make this also true.
But it always need not be the same assignment.
In general, no, but in this case, in this kind of reduction, it's the same assignment. And it's important that it's the same assignment because otherwise you can't go back. Right? So the z bar, you will introduce multiple such z's. Okay, and so you have to be careful. Okay. So, yeah, just think about this for a second. But these turn out to be equivalent.
So there is at least one assignment that is that satisfies that one.
In technically speaking, yes. But in this case, it turns out any assignment, if you just restrict it to these x variables, it's fine because you take any assignment to that which makes that satisfiable. By setting z appropriately, I can make this guy also satisfiable. The x parts will remain the same. Okay. Just the z will have to be set appropriately. Okay. So yeah, so it's good to think about these things and convince yourself that that you have a reduction in both directions. So okay, so this is relatively simple. And I was hoping to do this reduction also, but I don't think I'll have the time. But what I want to say is, so I wanted to say that, okay, so first you reduce the SAT problem, which we said by this Cook-Levin theorem is NP complete, to this 3-SAT problem. Okay. And 3-SAT is clearly a special case, so this shows that 3-SAT is NP complete. Now if I have a new problem, okay, so I'm considering this problem of independent set, this is a graph problem. So I don't have to go back and do reductions to and from SAT. Okay. So I can just, I have shown that 3-SAT is NP complete. Okay, so I can now start off with 3-SAT and say, oh okay, I'm going to just do reductions to and from 3-SAT. Okay. And you can keep doing this. Okay, so next class, I was hoping to be done this time, but next time we'll see this whole sequence of, so what I call chain of reductions, where we saw just the first part of this chain. Okay, so we saw SAT reduces to and from 3-SAT. Okay, and we'll see that this has a reduction from independent set in graph. And this can be reduced to and from what is called vertex cover. Okay. And this has things to subset sum. So this is one of these problems that we saw earlier in the class, where you have a bunch of numbers and you want to know if there is a subset of them that add up to some given thing. Okay, so we saw that you can try to do it using dynamic programming. Okay, but if the numbers are small, so if the numbers are big, it turns out to be NP hard. Okay. So this you can do subset sum, and this is related to this parallel machine scheduling and so on. But the takeaway from this is, the nice thing that NP completeness gives you is this, you don't always have to start with SAT. Okay, so all problems are equivalent to each other. So you start with any NP complete problem, you reduce to and from that problem, and you get NP completeness for your new problem. Okay, so that's the thing that you should keep.